Okay, when I was last speaking about chemistry, we were talking about the atomic bomb. And I was talking about it mainly because it had such a huge effect on the art and the culture and the history of the world. But I kind of skipped over a whole period of chemistry between the atomic bomb going back to the alchemists, right? So let's jump back to the kind of the end of alchemy and the beginning of the kind of chemistry era. So the last thing I talked about in alchemy was a guy named Robert Boyle, and he wrote a book called The Skeptical Chemist in 1661. And in that book, he made the first distinctions between alchemists, who were really kind of had the central passion of converting one kind of matter into another kind of matter, particularly lead into gold, or finding that secret of eternal life, medicinal chemistry, and the chemists, right? So he's broke these two people off, chemists and alchemists. Of course, him saying they were different didn't make them different immediately. Chemists kept practicing alchemy, and alchemists kept practicing chemistry. But during the 1700s, scientists really were desperately trying to make chemistry more of a thing, right? To advance the art. But there were limitations. One limitation was the equipment just simply hadn't been invented, right? The things we use to do chemistry today, for instance, the centrifuge, just wasn't a thing in the 1700s. But more importantly, chemistry suffered from being an art that wasn't cool. If you were a chemist, that meant you were either a crazy alchemist or you were kind of a low-class business person. It wasn't a social step you wanted to take to be a chemist. If you were a gentleman, scientist, you did geology. It was the blue-collar workers who did things with dyes and coal and materials. And that branched off into a really interesting area of chemistry and really kind of became what chemistry is today. And we'll talk about paints and dyes next week. But my basic point is chemistry wasn't cool, all right? So tellingly, one of the most important discoveries at the time came from a botanist, not a chemist. It was a guy named Robert Brown, and he noticed that grains of pollen, he loved microscopes, by the way. So Robert Brown noticed that grains of pollen suspended in some water, and he looked at them under a microscope, that they would vibrate. No matter how long he let the water sit there under the microscope to kind of settle, the pollen grains would still vibrate in the water. And he didn't know that this motion, now called Brownian motion, after Robert Brown, was due to the pollen bouncing off invisible molecules of water. But it was a crack in the door towards us seeing what atoms look like. Okay, so for the next 20 minutes, I'm going to go through the transition from alchemists and chemists being the same thing to chemistry becoming more respected as a science and bringing forth a number of really interesting, brilliant theories about what matter is and what atoms look like. Okay? Do you remember phlogiston from the alchemy? It's the element of fire, and a lot of early chemists still thought it was true. In fact, as late as the 1800s, chemists thought phlogiston was a real thing. They'd renamed it by then caloric, which is where we get the word calorie, the element of fire. So it was fluid heat. Some thought there were opposing forces, that there were calorics and there were frigorics. But many people just thought if something's cold, it just means that there's not very many calorics in it. Anyway, I bring this up because John Dalton, who is known as the father of atomic theory, he was working under this understanding that matter, the kind of chemical reactions of heat and things like that, were actually particles that were kind of embedded in in matter. So this idea that matter was made up of smaller things was already kind of out there. But what he theorized is that every piece of matter, every kind of element, is made up of smaller particles, kind of like billiard balls. And then these small particles, he called them atoms. He borrowed that word from an ancient Greek philosopher named Democritus, who also thought matter was made of small particles. But the kind of brilliant thing that Dalton brought to the table was that these particles had different sizes and different masses depending on what the element was. So he became the first scientist to really explain the behavior of matter and atoms based on their weight, essentially. He further explored the idea that these atoms would combine in kind of ratios to form new compounds. Now, he didn't always understand the ratios. He thought that water, by the way, was HO, right? So hydrogen and oxygen. He didn't understand the H2O part, for instance. But the idea that chemical reactions would occur when these atoms kind of reformulated into new combinations, right? A guy named Avogadro would pick up that torch. He noticed that 1 gram of hydrogen was equal in volume to 16 grams of oxygen, or to 35 grams of chlorine, and so on. They all had the same volume. And so he proposed that they contained the same number of atoms. But he didn't have any way of knowing how many atoms might be in that volume. He just thought they all had the same number. So Avogadro didn't have a number in mind, interestingly enough. And then his research, Avogadro's research, was promptly forgotten for like another 60, 70 years, right? Until 1860 or so. Anyway, so around the time that Dalton was working with this new brilliant vision of atoms making up matter, a guy named Humphrey Davy was working. And Davy discovered like a dozen elements, which was a huge number for the time. It was like a fifth of all known elements. And he did it through a process called electrolysis. One of his kind of graduate assistants was a guy named Michael Faraday, who became very popular later. And Faraday apparently coined the term electrolysis based on the word electron. It's a Greek word, which meant amber. And why amber? It's because if you rub a bit of amber, you get a static charge, right? Like rubbing a balloon on your head. So the word electrons or electrolysis or electricity comes from amber, where mosquitoes that have dinosaur DNA live. So the work of Humphrey Davy, and Michael Faraday basically showed that atoms carried electric charges. So we had a few things going on here. Dalton's work had showed us that atoms could be categorized by their size and their weight, right? So each different element had a different size, had a different weight in terms of its atomic structure. Davy and Faraday said, additionally, those atoms have an electric charge. It wasn't until 1897 that a guy named J.J. Thomson managed to isolate this charge. And he called this charged particle, a piece of an atom, he called it a corpuscle of an atom. That name was later changed to an electron, so I'll use that word. But others had proposed the idea that atoms had smaller parts. They just envisioned these smaller parts being the size of hydrogen, which was the smallest atom they knew of. But J.J. Thomson showed that electrons were thousands of times smaller than that. So to explain, though, if atoms are made up of lots of tiny negatively charged corpuscles or electrons, why wasn't the atom itself negative? Well, his idea was that these tiny little negative charges were embedded in this gelatinous kind of plasma positive charge, right? Like a ball of snot with little bits of negative charges in it, right? And he called this the plum pudding model. Actually, people called it that afterwards. But it was the plum pudding model, where you had a positive kind of blob with little negative electrons stuck in it, right? Kind of like blueberries in a muffin, right? So the plums were baked into the pudding, the plum pudding model. So in 1910, a guy named Robert Millikan at the California Institute of Technology, he figured out a way to measure how much the charge was on these electrons, right? Because J.J. Thomson's work gave us a good ratio between charge and mass, but we didn't know either of those values, right? So we had to figure out the mass or what the charge was to be able to figure out the other thing, right? So Millikan, what he did is he had two kind of charged metal plates, and he would spritz. At first he was spritzing water through it, but the water would evaporate too quickly. But in 1910, he figured out that if he spritzed oil droplets through it, they would hang on long enough that he could actually turn up or down the charge, and it would affect how the droplets were falling. And using this, he could measure how much charge electrons had. And so suddenly with this information, combined with Avogadro's work and so on, the number of atoms in a certain volume could suddenly be determined, their charge could be determined. Chemistry just suddenly started unlocking in 1910. The next year, you probably heard this name, Ernest Rutherford, the New Zealander. He showed in an experiment called the gold foil experiment. And what he did is actually had a sheet of gold foil, and he would shoot positively charged particles, alpha particles, through this gold foil. And most of them shot right through, right? Some of them were deflected slightly, but some of them bounced right back almost. And what this did is that kind of bouncing back could only be explained if there was something very concentrated, a ball of very concentrated positive energy. It was practically a point in space. So he suggested that it wasn't a plum pudding model, right? That most of it was empty space or electrons, where the positive particles are just flying through. Only a small amount of it was a kind of a small ball of protons. So he kind of switched the plum pudding model out, which made everything positive with some kind of negative dotted in it, and crunched the positive charge stuff down to what he called the nucleus. And so it's a positively charged ball of particles in the nucleus with electrons around it in space, right? And so Rutherford's picture of the atom was kind of like a miniature sun with electrons orbiting like planets, okay? So that was kind of the next big model. There remained a big problem, though. The nuclei of atoms were too heavy. Helium, for instance, has an atomic number of 2, meaning 2 protons, right? But it was twice as heavy as it should be for having 2 protons. So for a while, scientists were thinking, well, maybe the nucleus of helium and some other atoms have protons and electrons in them, kind of like a plum pudding model mixed with the solar system model of Rutherford. But it wasn't until 1932 a guy named Chadwick discovered the neutron. He realized that the helium nucleus contained 2 protons and 2 neutrons. And the neutrons didn't have a positive or negative charge, but they had mass. So they actually weighed that helium atom down, explaining why it was so heavy with only having 2 protons. But there's a problem with Rutherford's solar model. If the nucleus with its protons, and later they discovered it had the neutrons, but it's positively charged, right? And under Rutherford's model, you've got negatively charged electrons spinning around it. If you've got a positive center and negatively charged electrons, they're naturally, that orbit's going to want to decay closer and closer and closer until those electrons crash into the nucleus, right? And then boom, you have no atom, because positive and negative attract. A guy named Niels Bohr took Rutherford's model, and he explained why the electrons their orbits don't decay into the center. Basically, he said that electrons can only exist in certain levels, a ground state and an excited state. And that they could jump from these different levels by emitting or absorbing energy in fixed amounts. So for example, if an electron wanted to jump to an orbit closer to the nucleus, it has to emit energy, emit light. Conversely, when the electron wants to jump to a larger orbit, it has to absorb energy. It takes more energy to be further away from the nucleus. So Bohr found out through his experiments that the closer the electron is to the nucleus, the less energy it needs. But the farther away it is, the more energy it needs. And he actually numbered these energy levels, or shells, as they're sometimes called. The higher energy levels, the higher the number. The farther the electron is away from the nucleus, the higher the energy. He also found out that each shell can only support a certain number of electrons. So if you're close to the nucleus, that level 1 might, for instance, hold 2 electrons. If you went to level 2, that might hold 8 electrons, and so on. Now this Rutherford-Bohr model that kind of explained why the electrons don't collapse into the center is often what's given in science textbooks in high school and even in college, but it doesn't explain everything. For that, we had to turn to a new model. So throughout the years, our model of what the atom looks like has changed drastically. We began starting in the 1800s with Dalton's model, right? The billiard ball model, kind of very solid little balls that are the atoms, right? Then 100 years later, we had J.J. Thomson's model, and that was the plum pudding model, where we realized that there was a negative charge to atoms, and those negative particles, those corpuscles or electrons, he thought were kind of nested in a positive pudding. And then a decade later, we had the Rutherford model, which is what we often see on kind of like logos of the atom, the central nucleus with orbits of electrons spinning around. This got refined by Niels Bohr, who realized that they had to be in kind of levels, shells, energy shells, and that they wouldn't kind of decay into the center of the atom. The kind of current model of the atom is called the quantum model, and it was developed in 1926 by a physicist named Schrödinger, Erwin Schrödinger. And he took the Bohr model one step further. He used really complex mathematical equations that I don't understand to find out what the likelihood is of an electron being in a certain position at a certain time. This is the quantum mechanical model of the atom. So unlike the Bohr model, the quantum mechanical model doesn't define the exact path of an electron, but rather it predicts the kind of general location of the electron. And the model that we kind of conceptualize this with is with an electron cloud. So a nucleus surrounded by various different electron clouds of probability. Where the clouds are most dense, the probability of finding the electron is greatest, and on the other hand, the electron is less likely to be in a place where the cloud is not dense. So I don't want to leave you with the idea, that the Schrödinger model, the quantum mechanical model, is going to be what we're left with, right? That's not the model of the atom. That's the model of the atom that we know now. Science is all about making predictions and then proving them wrong, making new predictions, proving them wrong, refining, right, changing. Since the time that we, have discovered the proton and the electron and then the neutron. We've been bombarding atoms with, particles for a long time to kind of discover more about these subatomic particles inside the atoms. And we found things called quarks, right? Quarks are kind of smaller parts of protons and neutrons. And then the quarks themselves, the theory is that they're made of even smaller things, little vibrating strings of energy. And so the theories of what an atom is and how it's made continues, and it's ongoing, and it's what is kind of really exciting about the future of chemistry. Okay.